Hello Tony. So today we see I will know much about the topic which is called series. So in the last video I said that series behavior is analyzed by sequence of partial sums. Okay, so the general form of the series will be like this. For a sequence we represent like this, right? This means a set of a1, a2, a3. You no need to call it as a set, but it is terms, collection of terms. No need to be a set, because in a set repetition is not allowed, but in a sequence repetition is allowed. Okay, you represent a sequence like this, but this cannot be a set, because in a set, if it is represented by a set, then it will be just 2. This is a constant sequence. Okay, so now we see the general form of a series. Series means the sum of an infinite numbers. So we represent that sum, let's say those numbers represented by a1, a2, a3 and so on. If the infinite number of terms is added, then we represent the term, all the summation, we use this symbol. This is symbol for the summation, where an, this is a general term where n goes to 1 to infinity. Or we can also represent this one like this. Suppose a n plus 1. See here, n goes from 0 to infinity. If n is 0, it is started with a1, right? So like that, we need our series is starting with a1. So if n is 0, it is started with a1. So these two are the same, and you can change this variant. So you can change this. According to that, the initial term of a sequence will change. So that term, for suppose if you write a n plus 2, then the series summation starts from n is equals to minus 1. If n is equals to minus 1, then it is starting with a minus 1 plus 2, that is a1 to infinity. You can say that. So like this we can proceed to represent a series in different formats. Okay, otherwise you can also represent a series like this, like a summation a n plus 1, where n is equals to 1 to infinity. If n is 1, this summation starts with, if n is 1, that is a2. If n is 2, that is a3, plus and so on. So we are missing a term, that is a1. We are missing the term a1, so we add in the both ends. Okay, this type of representation is also there for a series. Here this ai or an can be any number, can be any number. So it can be a real number, or it can be an imaginary number that belongs to the real number. So real numbers, that is rational, irrational, integers, it can be anyone. Or it can also belongs to the complex numbers. We are yet to discuss the complex numbers which are of the form a plus ib. Okay, so this I is imaginary number. Okay, we can leave this one here, but you just know that this an can be any number. So we in the last class we discussed that the series and sequence behavior are interrelated. Okay, so how it is related we discussed, but we go to that briefly here. For suppose we are given with the series, for example we are given with the series an where n goes from 1 to infinity. See here, I did not write n is equals to 1 because there is only one variable here n, so it must go from 1 to infinity. Okay, so if this is so, then this is the summation of a1 plus a2 plus a3 and so on, right? So now we discuss a sum of the terms. First we take sum of first term. S1 is nothing but a1. S2 is sum of two terms, a1 plus a2. S3 is sum of three terms, a1 plus a2 plus a3, like this. If sum of k terms means a1 plus a2 plus a3 plus and so on plus ak up to the kth term. Okay, this summation. So see this, you can make s1 s2 s3 and sk and so on, all these as a sequence. Sn you can denote it like this. All the numbers here are denoted like s1, s2, s3 and so on. So when it reaches to the infinity, s infinity is equals to the sum of all the infinite numbers of the series represented here. Okay, this sequence is called sequence of partial sums. What do you call that? Sequence. Okay, this is called sequence of partial sums. So this is the sequence of partial sums. See here, all the sums are partial. Okay, so we cannot reach to the infinity, but we can only observe its pattern when it is reaching towards the infinity, right? So as far as we know, the sequence behavior, for suppose if you take a sequence, it can converge or it can diverge. So it can diverge to infinity or it can diverge to minus infinity. And there is third division, it can oscillate sequence, oscillatory sequence, oscillate. So in this oscillation there are two types. It can oscillate finitely or it can oscillate infinitely. Infinite oscillation, that means it can reach minus infinity and plus infinity as well as the sequence goes, as the sequence proceeds. So this is the behavior of a sequence. Now the same behavior can be analyzed, since the behavior of a series is determined by the sequence of partial sums, so it can also have an approach to this. Okay, the sequence may also have the same behavior. That means it can converge a series it can converge, okay, it can diverge, okay, it can diverge to either plus infinity or negative infinity. An oscillatory sequence a oscillatory series. So when you call that, it can oscillatory, so it can oscillate finitely. I am yet to find an example for a series which oscillates infinitely. I am yet to find that, but there may be infinite oscillation also. Okay, infinite oscillatory series. We can give some examples. A series which converges. That means if you say a series an converges, that means sum of all the infinite number of terms goes to a finite number. Let's say L. This L, for a particularly, you can say it is for example like 2. Okay, this L can be a finite number, for example 2. Then we say that it is convergent. Whether this number is positive or negative, it doesn't matter. So this series is convergent. Example for that is 1 by 2 whole to the power of n, where n goes from 0 to infinity. If n is 0, it is becoming 1, 1 plus 1 by 2 plus 1 by 4 plus and so on. So as this, so we can see that it is a geometric progression, right? 1 by 2, 1 by 4 and so on, all these are geometric progression, and it is an infinite geometric progression, infinite GP it is called, and its common ratio, 1 is multiplied by half, 1 is multiplied by half, this half is multiplied by half, so as to get to the 1 by 4. This 1 by 4 is multiplied by half, so as to get to the 1 by 8. So if this is like so, this is called common ratio. This half is called common ratio. If this common ratio is less than 1, then sum of the infinite GP is a by 1 minus r. Here a is the initial term and r is a is the initial term, r is the common ratio. Particularly here a is 1, the initial term is 1, so it is 1 by 1 minus the common ratio is half, so it will be 1 by 1 minus half is half, so it is 2, right? So the sequence of this GP is convergent to the 2. So all the infinite number of terms of this series is, if you add all the numbers, then it converges to 2. Okay. Similarly, we can make a series divergent to the infinity and negative infinity. So for example, for that is, let us give some example for that, which can diverges. For suppose diverges to the infinity. 1, let's say 1 to the power of n, where n goes from 1 to infinity. If n is 1, that is 1, it is summation of all ones. Okay. So if you add all those numbers, you will get to the infinity. So it diverges to the infinity. These are some simple series, so that you can understand there exist some of the examples for that. For suppose minus 1 to the power of n, where n goes from 1 to infinity. This is, if n is 1, this is the summation of all the negative ones, plus minus 1, plus and so on. So this will be diverging to negative infinity. All the summations will be infinite number of minus ones if you added, so it get to the minus infinity. Okay, this how it reaches is, we will discuss. Okay, we will much more go into the detail of the sequence of partial sums, but you can see that these are the simple examples. You no need any technicality, mathematical technicality, to know this summation is negative infinity. So I am presenting as simple as possible examples. Okay, oscillatory sequence. Okay, we will go to the oscillatory example for the oscillatory sequence. For suppose if a sequence is minus 1 whole to the power of n, where n goes from 1 to infinity. So this is minus 1 plus, if n is 2, then minus 1 whole square is nothing but 1, plus minus 1 plus 1, and so on. If you observe this, the sequence of partial terms, S1 is minus 1, S2 is, you add 2 terms, minus 1 plus 1, that is 0, S3 is, you add 3 terms, so that goes to minus 1, S4 is also 0, so it continues like this. So sequence of partial sums is having minus 1, 0, minus 1, 0, and so on, right? So this sequence is an oscillatory sequence between minus 1 and 0. It oscillates between minus 1 and 0 only. You cannot decide that whether it goes to the sequence reaches to minus infinity, which not minus 1 or 0. You cannot decide that. So you say that this sequence is oscillates between 0 and negative 1. So the series here is an oscillatory series, and it is finite oscillation. Minus 1 and 0 is a finite oscillation. Okay. For suppose next we give the example for the infinite oscillations, right? So we give an example for that also. Infinite oscillation of a series. For example, you take the series okay, minus n to the power of n, where n goes from 1 to infinity. So when you when you see the behavior of this series is, if n is 1, this is minus 1 to the power 1, that is minus 1, plus if n is 2, minus 2 whole square, that is 4. If n is 3, that is minus 3 whole cube, that will be minus 27, right? And the fourth term will be minus 4 to the power of 4, 16, that is 256, plus positive 256. Okay, now if you observe the sequence of partial sums, S1 is nothing but 1 minus 1, S2 is minus 1 plus 4 is 3, this is positive. S3 is okay, sum of first three terms, that is minus 24. S4 is something positive number, minus 24. If you remove minus 24 from this, okay, what do you have? That is 24, 2, 3, 2, 3, 2. So this is a positive term. So when you analyze this sequence, first it is minus 1, next it is positive, next it is negative, next it is positive. So if we can see that this sequence is not converging, but it also is not diverging to either plus infinity or negative infinity. It is not diverging to that. Okay, so you can see here this sequence of partial sums here, minus 1, 3, minus 24, 232, and so on. Next is a larger negative number than 232, that is minus 5 to the power of 5, okay, plus 232 will come here in the sequence of partial sums. So it will be very large and negative number. So as you can see, this sequence does not converge to any finite number and does not diverge to positive infinity, and does not diverge to negative infinity as well. So we can say that this sequence is oscillatory and oscillates infinitely. So it can in the odd numbers, if you take the odd number sequence, it is, that is odd terms of the sequence. This is minus 1, minus 24, and so on. All this sequence reaches to the negative infinity. If you take the positive terms, that means 3 even terms, 3 and 232, and next term, all these terms reaching to positive infinity. So we can say that this sequence oscillates infinitely. Okay, so all the examples are covered here. Now we go to deeper into how to find a sequence, how to use the sequence of partial sums to find what do you say, that series, summation of a series. So if we say that a sequence, or suppose if we have a sequence like okay, for series an where n goes from 1 to infinity, we have a series something like this. for this there exists equivalently sequence of partial sums Sn. Okay, so the behavior of these two will be the same. For suppose if you want to find, for suppose if the sequence is convergent, or you want to know the behavior of this series, then you find what is the limiting value of this sequence. Limit n tends to infinity the Sn. If you find if this is a finite L, a finite number, then you say that this sequence is convergent, or if it is either positive infinity, negative infinity, you say that this is divergent, this is convergent, or you cannot conclude that is either any one of these cases convergent or divergent, then you try to obtain whether it is oscillates finitely or infinitely. Okay, such thing is possible. That means how this is possible, that means the behavior of an is governed by the sequence of partial sums. So you assume S1, S2, S3 and so on. So you find what is, if n reaches the infinity, what is Sn? That is nothing but a summation of all ans, right? So we use this one extensively. Summation of a series is limiting value of its sequence of partial sums. We use this one extensively. So we solve some examples for that here. We solve some examples. For example, summation n by n plus 1, where n goes from 1 to infinity. If it is like that, where n goes from 1 to infinity, okay, so S1 is, this series is, you can see that the series 1, if n is 1 by 2, plus if n is 2, this is 2 by 3, similarly 3 by 4, plus and so on, and 4 by 5, plus and so on. You can see that 1 by 2, this is 2 by 3 greater than 1 by 2, and this is greater than 2 by 3, this is greater than 3 by 4, and this fraction is reaching almost to the 1. Okay, so it is not decreasing, it is increasing and reaching towards the number 1. So you can say that this sequence, so for suppose if you add half infinite number of times 1 by 2 plus 1 by 2 plus 1 by 2 plus 1 by 2, if you add those any finite number, if you add those infinite number of times, you will get to the, you will reach the infinity. Okay, you can say that the summation is reaching towards the infinity, any positive finite number. Okay, so S1 is half, and what is S2 is 1 by 2 plus 2 by 3. This is obviously greater than adding half and half, right? This is 1, because 2 by 3 is greater than half. Similarly, S3 is 1 by 2 plus 2 by 3 plus 3 by 4, which is greater than 1 by 2, 1 by 2, 1 by 2, this is 3 by 2. All right. So you can see this sequence of its partial sums are increasing. So this is half. Okay, Sn is term wise greater than half, 1, 3 by 2 and so on. This is 2 and so on. As this sequence diverges to infinity, so Sn also diverges to infinity. So you can say that limit n tends to infinity, Sn is infinity by the comparison. Okay, Sn is term by term comparison. This sequence here is lesser than the Sn, and the lesser sequence can diverges to the infinity, so as the Sn diverges to the infinity. That's how we give the reason here. And if you take the next example, example 2, the summation of minus 1 whole to the power of n goes from 1 to infinity. So we observe this is the sequence of, if n is 1, that is minus 1, if n is 2, that is positive 1, if n is 3, that is negative 1. So it will be continuing like this. S1 is negative 1, S2 is negative 1 plus 1, that is 0. S3 is, this is summation of first 3 terms, that is minus 1. S4 is, that is 0. Okay, so you can observe that this sequence minus 1 0 minus 1 0 and so on. So this sequence is not converging to minus 1 and neither not converging to 0 as well, but it is not diverging also. So this sequence is called oscillatory sequence, oscillatory. So, and it is a finite oscillation, finite oscillation. So the series oscillates finitely, minus 1 whole to the power of n, where n goes from 1 to infinity, oscillates finitely. You can write less, oscillates finitely. We can see another example here. How we are going through the examples, that how to use the sequence of partial sums to know the behavior of a series. Okay, so that is the third example. Here we have summation 1 to infinity 1 by n into n plus 1. So thus this series is so the first term here is, if n is 1, that is 1 into 2. The second term will be 2 into 3. The third term will be 3 into 4 and so on. So the first term here, second term, third term. So S1 can be, see, it can be written like this, 1 by 1 into 2. So you can say that this is nothing but a 1 by 1 minus 1 by 2. Okay, for the simplification purpose, in the further term, in the further S2 and S3 terms. So this is simply 1 by 2. Okay, S2 is nothing but 1 by 1 into 2 plus 1 by 2 into 3. So here this term can be expressed as 1 by 1 minus 1 by 2 plus this term can be expressed as 1 by 2 minus 1 by 3. So if we add all the four terms, these two cancel out each other, so we are left with 1 by 1 minus 1 by 3. This is nothing but 1 minus 1 by 2. So S2 is 1 minus 1 by 3. Similarly, S3 will be 1 minus 1 by 4. So if we continue like this, Sn is 1 minus 1 by n plus 1. So if we take the limit here, limit n tends to infinity, Sn, this one, is nothing but 1 minus 1 by infinity. 1 by infinity is nothing but 0. So the Sn, this sequence is converges to the 1. Okay. So the given series 1 by n into n plus 1 converges to 1. The sum of all the numbers, for example 1 by 1 into 2 plus 1 by 3, 2 into 3 plus 1 by 3 into 4 plus and so on, sum of all the infinite numbers, all of them added together, we get 1 by 1. So this given series is convergent to the 1. You can say something like that. So up to here we seen that a sequence series behavior analyzed by the sequence of partial sums extensively, and the series is not always as simple as we discussed in the examples, but to solve the complicated there are some ready-made examples or ready-made patterns of a series called geometric series and something more hypergeometric series. We will learn later. Okay. Before that, we discuss the algebraic properties of the convergent series. Okay. First, suppose the algebraic properties. Algebraic properties of convergent series. If there are two series an and bn are convergent, if there are two series that are convergent an and bn, so you can say that a summation of all the numbers of an converges to the L. Okay, for example, all the numbers that are in the series B converges to the m. So if these two convergent, then the summation of 1 to infinity an plus bn, this series converges to L plus m. Okay, that is nothing but, you can say that this is, you can write extensively like an 1 to infinity plus summation bn 1 to infinity. So if this is convergent, if these two are convergent, then this is possible. Okay, you can write implies. This is only possible if this condition is satisfied. For suppose if an minus bn, if you want to add, so we can take this negative also. An minus bn will be equal to summation n minus summation bn. And another property is, since we know that an is convergent, if you multiply each term by a constant c into an 1 to infinity, this is nothing but c into 1 to infinity am. Okay, so this is nothing but L, c into L. This series is converges to c into L. So this is, these two are the properties that if these two series are convergent, then this is possible. This is not the other way around. For suppose we will also give the counter example for that. Okay, for example, the counter examples will be like this. For example, you take two series. Okay, series, the first series is minus 1 whole to the power of n, where n goes from 1 to infinity. The second series is minus 1 whole to the power of n plus 1, where n goes from 1 to infinity. So if you see this series, the sequence of partial sums, the series is 1, negative 1 plus positive 1, negative 1, positive 1, okay, if you, the sequence of partial sums is like this: negative 1, this is, if we add 2, 0, negative 1, 0, and so on. So next thing is the second sequence. If you observe, it's, if you expand this one, if n is 1, that is even 1 plus, this is minus 1 minus 1 plus 1 minus 1 and so on. So each sequence of partial sums will be, first term is 1, if you add 2, that is 0, third term is 1, fourth term is 0, sequence of partial sums are like. So if we add this term by term, an plus bn, where n goes from 1 to infinity. If you add these, so each individual sequence is oscillates finitely. Each individual sequence is oscillates finitely. That means these two are not convergent. Okay. So, but if you add these two, the summation of minus 1 whole to the power of n plus minus 1 whole to the power of n plus 1, where n is equals to 1 to infinity. Okay. So if you add these two, if n is 1, this is 1 and that is 2, if you that is even, minus 1 plus 1, that will be 0. So that is this one is always 0 for any n. So 1 to infinity, summation of zeros will be 0, and you can, or otherwise you can see here, you add this. Okay, so this sequence is converging to 0, okay, but each individual sequence is not convergent, right? So what we are talking here, if each individual sequence is convergent, then the resultant sequence an plus bn also convergent, and its sum will be summation of those two individual limits, summation of the individual limits, but it is not the other way around. If this is, see here in this case, this one existed, the summation of an plus bn existed, but each individual sequence is not convergent, they are oscillating. The sequence is convergent, but each individual sequence is oscillated. So this is one of the counter example for this algebraic properties. This is only one direction. If this is possible, then this is must be satisfied. It is not the other way around. Okay, we will see one example for such sequence, which, okay, we will solve one example for a sequence for like a algebraic properties convergence series. Okay, if you write an example for this, for example, we know that 1 by n to n plus 1, this series converges to the 1. So 1 to infinity 3 by n into n plus 1 is converges to 3 into summation by this law, by this one, by the second one. You can see that, you can what do you say, that visualize that we factor 3 out of the summation. Okay, so this is, so 3 into all the sum, the entire summation is 1, so this is 3. Okay, for suppose if we have 5 by n into n plus 1 plus half to the power of n, where n goes from 1 to infinity. If we have a series something like this, how do we find? So we try to analyze the individual terms here. Okay, the series here 5 by n into n plus 1. So like in the above example, this one is converges to the 5 into 1, that is 5. Okay, here we add 1 to infinity, and 1 to infinity 1 by 2 to the power of n. This series we know that it converges to a by 1 minus r. A is nothing but half, and the first term of this series 1 minus, the common ratio is half, so it will be half by half, that is 1. So this series. So from the above law, that this series is converges to 5 plus 1, that is 6. So these are some of the examples of the algebraic properties of the convergent series. Okay, so you can look for the some more problems in the exercise section. Okay, so up to now we so far discussed what is a series and what is the sequence of partial sums, and how they are interlinked, and using the sequence of partial sums, how to find the summation of a series. We saw some of the examples there. We seen how does we reach to the conclusion using the sequence of partial sums, and later we came to the algebraic properties of the convergent series. So using this, how do we analyze? Okay. So we saw some of the, see this, when you first look at this one, it looks so huge and difficult task, but when we know how to degrade it to the ground level, in how to dismantle it, you can say that, then it becomes very simple, right? So to dismantle it, we use this theorem or this law, particular law. Okay, the algebraic properties of the convergent series, this particular law. So we stop here. In the next session we see some of the particular patterns, okay, particular families, or which shows the same behavior. We analyze some of the series there. One of them is geometric series, another one is hypergeometric or so. Okay, we go through, okay, we dig deep enough. Maybe in the next class we will be ending up with the theory. Later we solve some of the problems or exercise problems there. Okay, Tony, see you.